Namaskar and welcome back to our discussion on concrete engineering and technology. Continuing our discussion on mechanisms of deterioration in concrete, we were talking about alkali aggregate reaction. We will briefly go through some background, mechanisms of the reaction, implications of the alkali aggregate reaction, common tests for identifying reactive aggregates, and steps to prevent alkali aggregate reaction. Out of these, we have already seen the background information, mechanisms, some part of implications, and we have discussed the quick chemical test and the mortar bar expansion test, which are two of the more commonly used standard tests to identify reactive aggregates. So, we will continue our discussion from that point onwards, and we revise some of the fundamentals. We look at concrete as the multi-phase composite from the point of view of the fact that now we are not trying to do the volumetrics, which we did when we looked at this slide from the point of view of proportioning of mixes. Now, we will try to study the immediate neighborhood of a given aggregate. I have drawn the circle here around a coarse aggregate, which is easier to draw. Of course, it should be understood that when we talk of alkali aggregate reactions, we are talking of the reaction of fine aggregates or coarse aggregates. So, it is not really a matter of what aggregate we are talking about, in the sense that our fundamental understanding was that sand and coarse aggregate, that is the fine aggregates and the coarse aggregates, are both inert and do not take part in any chemical reaction. They do not react with the cement or its hydration products. They basically act as only fillers. This understanding is precisely what changes when we talk about alkali aggregate reactions. When the reactive components in terms of the minerals that comprise the fine aggregate or the coarse aggregate, they react with the pore solution formed as a result of the hydration of cement. These pictures here, they show some cracks which are formed on account of alkali aggregate reaction. We will go through the mechanisms a little bit in detail once again, but these pictures show us the kind of map cracking or an all round cracking that occurs in a structure when it is afflicted by alkali aggregate reactions. This is the picture which is from a pavement which was cast using concrete which had reactive aggregates. This picture here is a slightly different representation of what happens when alkali aggregate reaction occurs. We can see here that this crack here is a fairly wide crack. So, alkali aggregate reaction induced cracking in structures is not insignificant. It is not something which we would like to ignore, because such cracks have structural implications, they have durability implications, and so on. In this picture, in this part here, we also see the deposits of the white gel, that is the reaction product of the reactive silica and the alkali metals that are part of the pore solution. So, the gel that is formed, that absorbs water and gives rise to cracks, that gel moves around obviously in the cracks and fissures that are formed within the concrete, and this is a manifestation where we see that gel exuding to the surface of the structure. This picture we had seen in the previous discussion, where we saw that the alkali aggregate reaction is basically a reaction of the alkali in concrete, which is the sodium and potassium ions which are present as impurities in the ordinary Portland cement, and the reactive aggregate. The reactive aggregate means aggregate which has certain reactive minerals. Not all forms of silica is reactive, only certain minerals like opal, cristobalite, some forms of glass, they are the reactive minerals, and if they are present in the rock or the aggregate that we use, we have the aggregate which is reactive, and once they come together in a concrete, we have a reaction product, and this reaction product is basically a gel, and which in itself is innocuous, but it has the tendency to absorb water, and once it absorbs water, it swells and induces cracks of the variety that we saw in the picture just now. So, the alkali aggregate reaction in concrete leads to map cracking, reduction in the strength and rigidity or the modulus of elasticity of the concrete, poor durability and water tightness. This picture again is a schematic representation of the expansion that we see on account of alkali aggregate reaction over a period of time. This picture shows that most of the time the reaction tends to stop, that is, the expansion tends to stop after a certain period of time, and there is a limiting value to that expansion. This is something which is of interest to engineers, because in existing structures where inadvertently reactive aggregates were used, one may like to know whether the reaction is still continuing and we can expect further deterioration or more formation of cracks, or it has reached a situation where no more damage is likely, given the fact, of course, that alkali aggregate reaction cannot be reversed. Today we will spend some time looking at a model or discussing as to how this reaction tends to stop or slow down over a period of time. Other characteristics that we can see from that graph or from that picture is that there is an initial incubation period when no or very little expansion is seen, followed by some slow expansion, then rapid expansion, and finally a stoppage of the expansion after the limiting value has been reached. As far as implications are concerned, we talked about additional strains in terms of this reinforcing steel, and that is something which we will again talk about today. We will try to discuss a little more detail of that aspect and try to discuss it in the light that alkali aggregate reaction in reinforced concrete is something similar to that of introducing or inducing chemical pre-stresses in the concrete. The cracking in the surface concrete could promote ingress of deleterious materials such as carbon dioxide or chlorides into the concrete, and the map cracking reduces the modulus of elasticity of the concrete and its strength. Now, this here is a picture of, or is a close-up of another structure which is afflicted with the destructive alkali silica reaction, again from a pavement, and we can see that there is this alkali silica gel in the 2 millimeter void in a lapped splice from a pavement. The dark aggregate which is shown here, this aggregate, the dark aggregate which is shown here is a siltstone aggregate. So, this is the kind of gel that forms and gets deposited in the voids within the concrete, or if there are continuous pores connecting it to the surface, it also emerges at the surface, as we saw in the picture a couple of slides ago. This here is another picture of alkali silica reaction in the pavement with a dark metabasalt aggregate, and we can see that around these aggregates, all these aggregates here which are reactive, we can see a very clean description of a carbonated gel, and this is the gel that is formed on the rim of these aggregates, and that is what we were talking about the previous discussion and also today earlier on. The alkali aggregate reaction is usually very slow and proceeds through the process where the alkali in the pore solution permeates through the aggregates, and this process of permeation of alkali through the aggregates can be modeled as a diffusion process. Of course, the diffusion through the rock is not easy. Rocks are, after all, not all that porous, even though they are porous. So, the coefficient of diffusion in rocks is very, very small, and therefore, it takes time for these reactive or deleterious alkali ions to permeate through the rock. Once they have reached the rock, or even once they have reached the inside of the rock, they cause a breakup of the otherwise very stable silica bond and the lodging of alkali metals in the inert silica tetrahedron, along with the formation of complexes. As we saw from the previous pictures, the reaction really starts at the surface and gradually proceeds inside. So, basically we are looking at a process which starts at the surface, the reaction rim is formed, and gradually more and more alkali metal ions permeate through this reaction rim and also the rock and attack or modify the silica tetrahedron deeper and deeper inside the aggregate. Once these gels are formed on the surface or maybe inside the aggregate, they absorb water from the pore solution again, and this leads to swelling and expansion of these complexes and finally cracking of the concrete on account of alkali silica reaction. We must remember that water in concrete is available in plenty. It could be the water which is present from the time that it was mixed or cured, or it could be a replenishment by way of rainwater or any other form of water which is present. And finally, of course, as we have seen, there is a cracking in concrete due to the expansive pressures. Now, if we look at the simple model of aggregates, we had discussed this slide briefly in a previous discussion, and we now recapitulate that discussion and put it in light with the model that we have just talked about. We are looking at potassium and sodium ions in the atmosphere or environment around an aggregate. And if we take this aggregate to be spherical, we can assume that as far as the spherical aggregate is concerned, in the neighborhood we have sodium and potassium ions. Now, initially the reaction takes place at the surface, and we get reaction products that are formed and are deposited on the surface. After that deposition has taken place, for additional surface to be attacked, if this reaction thickness or the thickness of the aggregate which has been compromised, or where the reaction has already taken place and the aggregate has undergone the alkali aggregate reaction, this part is still unreacted. So, basically at each time step the reaction occurs at a fresh surface of the aggregate, and the surface of that reaction keeps shifting inwards. So, now over a period of time, if the reaction products are dense enough, then the permeation of the sodium and potassium ions through those reaction products would become more and more difficult, because the reaction products are being formed and are deposited within the pore structure of the rocks, which as it is have pretty low porosity, as a result of which the reaction really ceases. Arguing this point slightly differently, if we have a reaction where A and B are reacting to form a product C, when will we say, or when can we say that the reaction has stopped? Either A should finish, that there is no more A, or B should finish, that there is no more B, or the A and B should not be able to come in contact with each other. And in that case, even though there may be A or there may be B, but there may still be no reaction. So, in the case of alkali aggregate reaction kind of in the scenario like that of alkali aggregate reaction, the situation translates to, do we run out of reactive minerals in the aggregate? The answer is pretty much no, because there are enough aggregates and therefore enough reactive minerals within the concrete for the reaction to go on. Do we run out of alkali metals in the pore solution? The answer could be yes or no, depending on what is the amount of alkali which is present in the pore solution to begin with, and that is related to the amount of alkali present in the cement and the quantity of cement in the concrete. A third possibility that, well, we still have reactive minerals, we still have alkali in the pore solution, but this thickness has reached a level where it has made it very difficult, close to impossible, for the fresh surface to be approached by the alkali present in the system, and that would be the place when the reaction would cease. And this simple qualitative description is what we can offer to explain why the expansion of the alkali aggregate reaction follows an S-curve kind of a behavior. Initially, when the sodium and potassium ions are permeating, this may take some time when the reaction picks up, and gradually the rate of reaction increases, but at a certain point in time it ceases. There is another characteristic, depending on what the aggregate configuration is, the rate of reaction is very rapid initially, and that also can be built into our system or into the model that we talked about when we say that initially the surface area available is large and the reaction proceeds rapidly, but as the reaction proceeds, its rate slows down as it becomes more and more difficult for the alkali ions to diffuse into the aggregate and cause or bring about further reaction. So, with this kind of discussion, we can summarize that the reaction ratio, which is essentially a ratio of the volume of aggregate which has been reacted with to the original volume of the aggregate, that would depend on parameters such as the diffusion coefficient K of the rock, the concentration of the alkali C, the time, and the size of the aggregate. Putting it slightly differently, the extent of reaction and expansion on account of alkali aggregate reaction can be looked upon as a complex function which is related to the alkali present, that is the alkali content in cement, the reactive silica present, the surface area available, which governs the total concentration of alkalis per surface area or the per unit surface area of the coarse aggregate or the fine aggregate, the reactivity of the minerals, and the environmental conditions like temperature and humidity. Now, let us try to discuss the issue of alkali aggregate reaction in reinforced concrete. Before we get into the reinforced concrete and the discussion of alkali aggregate reaction, let me digress a little. Before we continue our discussion with reinforced concrete and alkali aggregate reaction in that concrete, we will make a digression. We will talk a little bit about pre-stressed concrete, and we will soon see what is the relevance of this. What happens in pre-stressed concrete? If we take a beam which is supported like this and loaded the way it is shown, the beam sags like this, and if we are able to have forces in the reinforcement which are tensile, then what we are basically doing is causing this beam to hog without the action of external load. And if the beam gets into a hogging position before the application of load, then once the load acts, this hogging tends to be balanced, and that is a method commonly used to overcome concrete's weakness in tension. And there are two basic methods of applying this pre-stress, when one is pre-tensioning and the other is post-tensioning. Now, in pre-tensioning, what's done is that we have a steel and we tension it. We have these jacks through which we pull the steel to a certain location, and then we cast the concrete. And once the concrete has been cast and it has hardened, we cut the steel tendons, as a result of which the beam tends to hog the way it is shown. So, basically what is going on is the fact that concrete, if it was not reinforced, would like to go back to its original position, which is something which is prevented by the presence of steel. And since the degree of restraint at the top surface here is smaller than the degree of restraint at the bottom, the beam tends to hog. And if this hogging is not controlled, we could have cracks initiating at the top the way it is shown here. Now, if we look at the post tensioning system, we cast the concrete without any steel, then we have a steel tendon which is inserted, and a jack is used to introduce tension in the steel, and the steel is allowed to go back to its original position using anchors. Now, once the steel wants to go back to its original position, that is something which is resisted by the presence of all this concrete here. As a result of that, the situation is very similar to something which is shown here. The beam tends to again hog. Now, as far as alkali aggregate reaction and the reinforced concrete is concerned, the situation is something similar. Now, the situation in the case of alkali aggregate reaction in reinforced concrete is something similar. Once the concrete expands on account of alkali aggregate reaction, this expansion is resisted by the presence of the reinforcement. If this reinforcement was centrally placed, then all that will happen is the amount of expansion would be reduced compared to the amount of expansion that would take place in plain concrete. But we know that in concrete members, particularly beams and slabs, the reinforcement at the bottom is more than at the top in a normal simply supported cases and so on, apart from cantilevers where the situation is reversed. But not getting into that detail, the fact remains that the degree of restraint to the expansion is higher where the reinforcement is higher, and that is what would cause a situation which is close to this. There would be an additional strain in the reinforcement, and there would be a hogging as far as concrete is concerned. Therefore, now we know that as far as the pre-stress concrete is concerned, the pre-stress is introduced in the concrete when we cause stresses in the steel, and those stresses in the steel are transferred to the concrete. In the case of alkali aggregate reaction in reinforced concrete, the stresses are generated on account of expansion of the concrete and transferred to the steel. The net result is still the same, hogging of a simple RC beam, and that is something which we must keep in mind when we try to study the strains that are formed in the steel on account of alkali aggregate reaction. Something very, very similar would follow in a normal concrete if we were to introduce chemicals in the concrete which cause expansion, and that is what is called chemical pre-stressing. In chemical pre-stressing, we introduce expansion in the concrete through the presence of some chemicals, and that expansion in concrete is again resisted by the reinforcement present, and we get a more or less similar situation as we get in pre-stressed concrete. With this now, we come to the last part of the discussion on alkali aggregate reaction, which deals with countermeasures against this phenomenon or this mechanism of deterioration as far as new structures or new construction is concerned. We will try to deal with this problem of countermeasures against the alkali aggregate reaction at two levels. One is for new structures, where we can more or less take steps to ensure that the effects of alkali aggregate reaction are kept to a minimum, the deleterious effect is minimized, and that in the case of existing structures where inadvertently reactive aggregates were used and there is a problem of alkali aggregate reaction. So, as far as new construction is concerned, if we revise our fundamentals, alkali in concrete and reactive aggregate gives you reactive material, and that is the thing which we need to control. So, the options that we have are very limited. As far as alkali is concerned, reduction of alkali in concrete is more or less the only option that we have. If we are able to control or we are able to reduce the amount of alkali in the concrete, we have overcome the problem of alkali aggregate reaction. Or we may simply eliminate reactive aggregates from use. Now, this is something which is easier said than done. We have talked about it earlier that the choice of aggregates is not something which an engineer is completely free to make, at least from the point of view of economics. Aggregates in a particular region may be reactive, and therefore, it implies that all concrete in that region which uses aggregates from that quarry or that particular area would finally have reactive concrete, unless we are taking measures to control the reaction. It may not be always economically possible, but that is the only choice that I have as an engineer. As far as reduction of alkali in the concrete is concerned, we have the option of using low alkali cement, using admixtures. We will try to see that in a moment. As far as the elimination of reactive aggregates is concerned, we can use these methods to evaluate the reactivity of the aggregates, and finally, of course, use non-reactive aggregates. Using non-reactive aggregates is perhaps the best option. That gets rid of the problem at the root itself. Mixing reactive and non-reactive aggregates. Now, this is a very interesting option that emerges as a compromise between economics and technical understanding or technology. If we have the constraint of having to use reactive aggregates or having to use aggregates available in the neighborhood which is reactive, can we mix some part of it with non-reactive aggregates which may be brought from us, which may need to be brought from a greater distance, and what will be the impact of that mixing on the ultimate expansion? That is something which we need to study, but that is an option which is worth exploring. Controlling the alkali content in concrete. Now, this can be done using low alkali cement, and just to recapitulate what is low alkali cement. Low alkali cement is defined in terms of the Na2O equivalent of the cement, and that is nothing but the Na2O that is present in the cement plus 0.658 times the K2O, that is the potassium oxide. So, the sodium oxide and a certain fraction of the potassium oxide contribute to define what can be called the equivalent Na2O in a cement. Now, once we have this number, specifications as far as cement is concerned define a low alkali cement as something as a cement which has less than, let us say, 0.6% of equivalent Na2O or 0.7% equivalent Na2O and so on. We could use supplementary cementitious materials as a substitute for some part of the ordinary Portland cement. We could control cement content. So, basically the bottom line as far as all these methods is concerned is the following. We have concrete which has a certain amount of cement, let us say 300 kgs, and this cement, let us say, has 1% of equivalent Na2O. As far as this concrete is concerned, this concrete now has 3 kgs of equivalent Na2O per cubic meter of that concrete. In order to control this 3 kgs per cubic meter of equivalent Na2O, we can use any of these options. If we are using a low alkali cement, what we are doing is that instead of this 1%, if we use a cement which has 0.5% of equivalent Na2O, we would have reduced this 3 kg to 1.5 kg. Similarly, if we were to use supplementary cementitious materials, whether it is blast furnace slag or it is silica fume or it is rice husk ash or it is fly ash, what we are doing is, instead of this 300 kg, we are able to reduce it to 250 kg or 200 kg. By that token, even if my equivalent Na2O remains at 1%, now let us look at the option of using supplementary cementitious materials. Going back to the previous example, when we said that my Na2O is 1%, my unit cement content was 300 kgs in a cubic meter of concrete. If I am using supplementary cementitious materials which allow me to reduce this cement content to say 200 kgs, then even if my equivalent sodium oxide content remains at 1%, my total alkali content in the concrete would only be 2 kgs per cubic meter instead of the 3 kg per cubic meter that I had if I was using 300 kgs per cubic meter of cement. Now, how is controlling cement content different from using supplementary cementitious material? It is different in the sense that in the previous example we said that instead of 300 kgs of cement, we will use 200 kgs of cement plus another 100 kgs equivalent of cement in terms of fly ash or slag or any other supplementary cementitious material. When I talk of controlling cement content here, what I am saying, or what the engineer wants to do, is to reduce the cement content required. Instead of 300, we reduce the cement content required to, let us say, 250 kgs. How do we do that? We do that by using, let us say, chemical admixtures. That is, we go back a step further and say that if the water demand that I have for a certain workability was 200 kgs and the water cement ratio that we needed was, let us say, 50%, my cement content required there would be 400 kgs. But if I am able to reduce my water demand from 200 kgs to, let us say, 180 kgs, at the same water cement ratio, I will use only 360 kgs of cement. Basically, this is the cement reduction that we are talking about, controlling the cement content. That is, we are trying to reduce the cement used. In this discussion here, we are not really reducing the cement content. We are reducing OPC content all right, but we are not reducing the equivalent cement content. When we are talking of controlling the cement content here, what we are talking about is the reduction in the equivalent cement content itself without using mineral admixtures. In this side we are using mineral admixtures, in this side we are not using mineral admixtures, and yet we are able to get the same result. We are able to reduce our cement consumption, we are able to reduce our cement content in the concrete. And finally, we have the option of preventing the structure from coming in contact with water. We discussed earlier that the gel may be allowed to form, but it is the expansion of the gel which has to be prevented, and that can be done if we effectively prevent the structure from coming in contact with water. It may be possible in certain cases, it may not be possible in certain cases, but that surely is an option which is available to the engineer. Now coming to the countermeasures against alkali aggregate reaction in existing structures, all that we can do is to try and control this part, because the reacted material is already within the concrete. The potential to form reacted material is already within the concrete. We cannot change the aggregates there, we cannot remove the alkali within the concrete, and therefore all that we can do is prevent water permeation, and that we can try to do by applying a coating on the concrete surface, and that is an option which is available even in fresh construction. In a new construction, we can try to apply a coating on the surface of the concrete which will prevent ingress of water into concrete. If we are able to do that, fine, but that is more or less the only option that is available to control alkali aggregate reaction in a existing structure. In this context, we must also remember that as far as the coatings is concerned, they are often having resins in them. These resins tend to deteriorate due to the ultraviolet rays, and when they are exposed to sunlight for long periods of time, surface portions of the resins tends to fall off and reduce the thickness. So if we are using coatings, we should be also concerned about the durability of the coating itself in terms of its ability to withstand ultraviolet radiation. We talked about the option of mixing reactive and non-reactive aggregates. This here is a picture of what is the likely expansion that we get if we vary the reactive aggregate ratio from, let us say, 0 to 100%. That is, we do not use any reactive aggregate, and still we will get some amount of expansion for different reasons, and using 100% of the reactive aggregates. We must remember that we get what is called a pessimum content. The pessimum is a opposite of optimum, because that is something which we do not really want. The pessimum content is the content of reactive aggregates where the expansion is maximum, where we get even more expansion than what we would get if the reactive aggregates were to be used only. That is, only the reactive aggregates were to be used, we get this kind of an expansion here, but if only a small amount of non-reactive aggregates were to be mixed, the expansion would be higher. This is something which should not be lost sight of if we are choosing to mix reactive and non-reactive aggregates, because mixing non-reactive aggregates does not necessarily or may not necessarily bring about a reduction in the total expansion. If we try to do a numerical model, we would understand this in terms of how the amount of alkali available in the concrete changes as the surface area of the reactive aggregates changes. As the reactive surface area reduces, and that is what will happen if we use some amount of non-reactive aggregates without changing the amount of alkali, the concentration available for the attack on the reactive minerals would be larger, and therefore, the reaction would tend to cause more expansion. However, if at the end of it the reactive area becomes smaller than a certain value, then it is not enough to be able to cause as much expansion. If the reactive aggregate surface area was to reduce below a certain value, then of course the phenomenon changes and the total expansion is now being governed by the surface area available and not the concentration of the alkali per surface area, which is governing in the case when the surface area was being reduced in the initial part, that is here. Now, with this we come to a close of the discussion, and as we usually close, we can do some more work and study a little bit about chemical pre-stressing, and that is what we talked about in our discussion today. We can talk about or study more about the porosity and the mineralogy of rocks, which will give us a better understanding of the alkali aggregate reaction itself. We can study the quarries in our neighborhood and the properties of the aggregates there. We could look at the maps of different regions of the world which have been identified as producing reactive aggregates. We could study the research material which is available on topics such as the alkali aggregate reaction in reinforced concrete, use of cores to identify the remaining expansion in existing structures, and study the expansion on account of AAR with different cementitious mixes. And that is the kind of discussion which we were doing, or which is relevant from the point of view of controlling the expansion on account of alkali aggregate reaction by manipulating the cement content or the alkali content in the cement, controlling the cement content, using chemical admixtures or mineral admixtures to control the overall alkali content in the concrete. And with this, we conclude our discussion for today. Thank you.